Hello, class. Alright, so we're going to do another problem. We're going to derive an equation called the range equation. And so the problem is, we're going to fire a projectile with an initial velocity v0, say an angle theta above the horizontal. And we want to know how far this projectile is going to go. Now, this is a very specific problem where the projectile is launched and it's going to land on the same level that it was launched from. So if you have, say, a problem like this, say you fire a projectile off of a cliff and, it's going to land a certain distance away from where it was launched, you cannot use the range equation here because it's, landing in a different height than it was launched from. And similarly, if you fire a projectile like on a hill, so if the ground isn't level and you fire a projectile, again, the range equation would not apply to either of these cases. So again, it's one of those things I have to definitely emphasize. The range equation only applies to this case, where it lands at the same level that it was launched from. Okay, so now that we've stated the problem, we want to find out where it's going to land. So we're going to go through our kind of procedure. Let's say the origin is the launching point, and it's going to land at point A, where it'll have coordinates r0, where r is the range, and it's, again, this is, here we can call this point 0, 0, where it's launched from. This is r0. And so what we're going to do, we have our basic equations to describe the position and velocity of the object, and I made a table that we're going to fill out as well. However, in this case, let's start out filling out our table. The initial position, it's launched from the origin, so the initial position, it has coordinates 0, 0. Now the acceleration, again, we're saying up is our positive direction, and like usual, we are ignoring air resistance, so not maybe the most realistic problem, but we have 0 and minus g. But now the velocity, we're given the speed of the projectile and its angle. And so what we have to do, let's draw the initial velocity where we've got the speed of the projectile, or the magnitude of the velocity vector, and this is our angle theta. So we want to break this up into components. So we've got cosine and sine. So let's write those down here. V0 cosine theta and V0 sine theta. And all we're actually going to need here is the position equation. So let's start it out. So again, we've got 3 terms, 3 rows, and there's that correspondence between them. And so again, I'm not going to erase it like last time, but we're going to first look at the x-coordinate of this projectile as a function of time. So we look at the x column. This is all we can plug in, these 3 numbers. So the first term is 0. The second term, we have V0 cosine of theta times t. And the third term involves acceleration. That one is 0. So we're done with x. Now for y, we have 0 to start with. And then we've got V0 sine of theta times t. And then the third term is minus 1/2 gt squared. So yeah, just plug in a is minus g, so we put the minus sign in front. And so again, this is the path of the particle. So again, this applies to all these points along the path from when it's launched until when it hits the ground. But we want to look at this particular point A, where it hits the ground. So let's just plug in the coordinates. Remember, there's 3 coordinates here. there's x, y, and t. So for x, we have r equals v naught cosine of theta. And the time would be this particular time, ta, which we don't know. But yeah, the y-coordinate is 0. So we plug in, again, just the time coordinate as well. And so again, this is the general equation. This just applies at point A. And remember, our goal is to solve for r. So to do that, we have to find ta. Now, and again, we're going to get t from the second equation. Now, what I'm going to do is, to solve this, let's start by just rewriting a little bit. We can say 1/2 g ta squared equals v naught sine of theta times ta. So I just moved this term to the other side. And now what I'm going to do is divide by ta. Now again, ta is an unknown variable. So you always want to be careful when you're dividing by a variable if you don't know what it is. And the reason why is it's possible that variable is 0. And you might not know that, and you cannot divide by 0, so that can cause problems. But here, time, this is time. So we launch it at t equals 0, so this time is definitely not 0. So we can safely divide by ta. I'm just going to do this. Just to save a little room. We'll just erase one on each side. And so now we can solve for ta. So we have 2 v naught sine of theta divided by g. Do it like that. Okay. And so now we're almost done, really. We just want to plug it into this equation now. And then clean it up a little bit. So we have v naught cosine of theta times 2 v naught sine of theta divided by g. And we can clean this up a little bit. We can say, I'm going to write it in a particular way. We have v naught and v naught, so that's v naught squared. And then times 2 sine of theta times cosine of theta divided by g. You might wonder why we didn't put the 2 in front. Normally you'd put a number in front of all the variables, but there's a reason which will be clear later. Now in a sense, we could stop here almost, because presumably, let's say we know the initial velocity and theta, everything on the right side is known and we can plug things in. However, we want to do one more step for 2 reasons. One is it'll make the calculation a little bit easier. But 2, with this equation the way it is, we can solve for it. We can plug in v naught, we plug in theta here and here and here. But what if we had an alternative problem, and this is a very realistic one. Like say you're launching a projectile and you want to hit a target. Like say you're firing a cannon and you want to hit a target. Now the cannonball is going to come out of the barrel of the cannon with a particular velocity. And so aiming it, you have to select the angle. So maybe a more realistic case, instead of just knowing how far particles or projectile is going to go, maybe you want to aim this projectile by selecting theta. And so you'd have to solve this equation for theta, which is very difficult the way it's written, because it shows up in 2 places. So how are we going to solve this for theta? And so, fortunately, there's a little trick we can do. Now, this is something you may have never seen before. And like if you've taken trigonometry or pre-calc, you've definitely seen this. But I'm going to write down this formula. sine of 2 theta is equal to 2 sine of theta cosine theta. So that is an equation which might have seen in trig. And I'm not going to try to prove it here because what I'm going to do, I don't like just giving you an equation and say, here it is. But at the very least, we can kind of test it. Let's make up an angle. You don't want to make up like an angle like 30 degrees or something, because that's a special angle. So let's just pick an angle like kind of like 22 degrees. I'll write it here and then erase it. Let's say theta is 22 degrees. And again, this is no way to prove something mathematically, but it's physics class, so why not? So let's start out by taking sine of 44 degrees. And what I'm getting is 0.695. And then that's equal to 2. So let's do sine of 22 degrees, which is 0.375. And then cosine of 22 is 0.927. So I'm going to multiply these three numbers on the right side. And what I'm getting is 0.695. So it works. And again, that is no way to prove a theorem or something like that, just showing it works for one particular number. But if we pick a random number, that's pretty good. And again, this is a well-known formula, so we're just going to use it. And so with that, we can write our range equation this way. So basically we have v naught squared over g, and then this part here is sine of 2 theta. And this is a much better way to write the range equation, because you can solve this equation for theta by taking an inverse sine. Actually, if you take an inverse sine, what you'd get is 2 theta, and then you'd have to divide by 2. So maybe we'll do an example of that. But first, I want to talk about an important consequence of the range equation. And again, just kind of just randomly remind you again. You can only use this equation if the particle is going to land at the same height it was launched from. And I say that because students love just having a kind of problem where you look up the equation and you have all the right variables, and so you can just plug it in and get an answer. But again, you want to make sure you're using the equation properly, and so it only applies to this one particular problem. But let's say your goal is to get the maximum range out of this projectile. What angle would you select? And I'm just going to state the answer and then explain why it has to be. So a 45-degree angle would give you the maximum range. Oh yeah, so again, landing at the same level it's launched from, also neglecting air resistance. So a 45-degree angle will give us the maximum range. Now, why do I know that's the case? Well, if theta is 45 degrees, sine of 2 theta is sine of 90 degrees, which is 1. And so if we select theta as 45 degrees, then the range is going to be v naught squared divided by g. And we'll never get more than that, because the range in general is v naught squared divided by g times something, and sine of any angle is never going to be greater than 1. So if we pick 45 degrees, this term is going to be 1. We're never going to make sine of 2 theta bigger than 1. And so Yeah, that's the maximum range you can get by selecting a 45-degree angle. Now, I want to make a problem. Let's pick a V naught, a particular value. Let's say 20 meters per second. So we can expect the maximum range. That would be 400 meters squared per second squared, divided by 9.8, which we can approximate as around 10. And remember, the units, we have meters squared over seconds squared, divided by meters per second squared. That would give us a range in meters. And so in this case, our max would be around 400 divided by 10, or 40 meters. Okay. Now, I want to do a problem. Let's say you want to find an angle so that, let's say, what angle should we select so that we get a range of 30 meters? Again, that's a possible range that we can get. So there should be a solution here. And actually, there may be two solutions. We'll see. So let's, basically what we're trying to do is solve for theta. And again, it's going to involve an inverse trig function, so we do want to be careful about this. So let's rewrite this equation. And we can say sine of 2 theta is equal to GR over V naught squared. So just algebraically, solving for it. And again, very important check. This is a dimensionless number. Here we have meters per second squared times meters divided by meters per second in parentheses squared. So we have meters squared per second squared and meters squared per second squared. So we have sine of 2 theta is just equal to a number, and it has to be that way. You can never have sine of theta equals like a meter or something. So that's a good check. And let's actually find out what this number is. So here we have 9.8 times 30, and then divided by 400. So this is 0.735. Okay, now I mentioned that we want to be careful anytime. So the next step will be taking the inverse sine. But again, we want to be very careful about doing that. So what I'm going to do is I'm going to plot sine so we go it's going to look something like this. And again, you know what, let me plot the entire, yeah, actually I think we might just get one angle here. So, yeah, I don't think we have to worry because we're in this right range here. Oh wait, we have a 2 theta issue here. So if this is 2 theta, yeah, I think we're good. I don't think we'll have any issues with taking an inverse sine. So let's, yeah, we should get a unique solution. So anyways, let's do this. So again, what we want to do, the way to think of it, is sine and inverse sine undo each other. So if we take the inverse sine of both sides of the equation, we'll have the inverse sine of 2 theta equals inverse sine of 0.735. And then the sine inverse of the sine, those two kind of undo each other. So we get 2 theta is equal to the inverse sine of 0.735. Oh, take that in wrong. Sine inverse of 0.735, which is 47 0.3 degrees. So that's what 2 theta is. So that would mean that theta is 1/2 of that, or 21. Okay, 47.3. Yeah, 23.7. Round it off to that. Okay. So that's what angle. Now, I want to think about this a little more because, actually, yeah, I think there should be 2 solutions here. So if you have a low angle, it's going to go like this and hit the ground here. I think there should be a higher angle as well. That would look like that. So, yeah, okay, so I plotted it, just over where sine is defined. I think the issue is this 2 theta. So 2 theta has to be in this range. Here, we get an angle less than 45 degrees, but there should be an angle above 45 degrees that's going to work as well. So I'm going to plot this. Let's look at sine. Let's look at an xy plane, or here x and sine of x. So this is 90 degrees, and this is 180 degrees. Now theta has to be between 0 and 90 degrees, but 2 theta then could be anywhere from 0 to 180 degrees. So basically we want sine of 2 theta is 0.735. So remember the peak here is 1. So yeah, 0.735 would be here. So yeah, we are going to have 2 solutions. So the first one is going to occur when 2 theta is equal to 47.3 degrees. But then we'll have another one that's over kind of on the other side, between 90 and 180 degrees. And the inverse sine will not tell us that angle. So we have to figure it out a different way. And one thing we could do is look at a unit circle. So I'm going to erase this. Let's try a unit circle. And remember, the sine is the y component. So there should be 2 points between 0 and 180 that have that same y component. And so here, this angle is theta. This angle should be the same. And so if we want to find, starting from here, again, this angle was 47.3 degrees. So this angle here is 47.3 degrees. So if we start from the positive x-axis and go around, this angle would be 180 minus that. So let's see, 180 minus 47.3. So I'm also going to, let's check this angle. Let's say theta equals 132.7 degrees. And let's take the sine of that. Sorry. Okay. So let's take the sine of 132.7, and what we get is 0.735 degrees. So remember, before we took any trig functions, it's like we're looking for solutions to this equation. Sine of 2 theta is 0.735. And a kind of trivial way to find that solution is to take the inverse sine, which gives us this angle. Here. But another solution is given by this angle, 2 theta is 132.7 degrees, and you can check it just by taking the sine of that. And you get 0.735. That's a solution as well. And that's a valid solution because if we divide by 2, remember the actual angle has to be between 0 and 90 degrees, but we're taking, we have a 2 theta here. So if we divide by 2, 132.7 divided by 2. So another angle is 66.4 degrees. So again, my recommendation whenever you have like sine of something equals a number and you want to find what's in the parentheses here, I highly recommend drawing a graph because then you can clearly see there should be 2 solutions between 0 and 180 degrees. And then if you divide by 2, both of these will be in that 0 to 90 degree range that we need. So, yeah, these are the 2 solutions. Let's call them theta 1 and theta 2. Yeah, they will, they'll both give you this same range. I think it was 30 meters. Okay, so again, just always be careful with inverse trig functions because it's very easy to miss that. But if you just plot the sine function over an appropriate range, then you can, you can see that there's 2 solutions. But we'll stop here. So that's the range equation. Very useful, but kind of limited use in a way as well, because you can only use it in that particular case where it lands at the same level that it's launched from. Okay.